This is video 35 from digital-university.org. In this video, we're again going to compare the mesh current analysis technique with the node analysis technique. And then in the next couple of videos after this series, we're going to look at supernodes and again consider circuits that have multiple current and voltage sources together in the same circuit. Now here for this problem, what we want to do is we can solve this quite readily. For this circuit here, we can determine the circuits through all the resistors using the mesh current analysis technique, but we can also redraw the circuit and analyze it using the node analysis technique. And that's what we're going to do in this video and kind of compare and contrast once again the two techniques. And remember back in video number 22 when we discussed source conversions that a circuit like this is equivalent. These two circuits here are equivalent in terms of the current and the power that they deliver to this resistor here. And here, of course, we just have a voltage source and a resistor in series. This resistor could just simply be the resistance of the voltage source. But we have a voltage source and a resistor in series. If we take the value of that voltage source and divide it by that resistance, and that's the magnitude of the current in this circuit, where now this resistor is in parallel with the current source, then this will deliver the same amount of current to this resistor as this simple circuit does. Now, here we have in the bottom part a variation of that. Or let's go back up to here, where now we have the resistor in series with the voltage source as we did before, and here's our load resistor, but now here we have another resistor in series. And in this case, if we divide the voltage source by the sum of these resistors and use that as the magnitude of the current in this circuit, where now this resistor in series, the value of it is the sum of these two resistors, then the current that goes through RL in this circuit is identical to the current that goes through RL in this circuit here. So now what we're going to do is take a look at our original problem. And here we can redraw it then, where the current source is equal to the voltage source divided by the sum of these two resistors. So we have 240 divided by 12, that's 20, and then the sum of these two resistors, 12, is in parallel with that current source. So this circuit and this circuit are identical, but as we encountered in the last video, we have to be careful because here the current that flows through this resistor is not the same as the current that flows through this resistor. So we have to think of it as, in this sense, that this is like the source circuit, and we're plugging this into the source circuit. And in this case, this is the source circuit, and we're plugging all of this into the source circuit. So for on this side of the figure, what happens here and what happens here is identical, but when it comes to considering these two resistors, we have to be a little bit careful about it, and we'll address that part of the problem when we get to it. Okay, let's take a look at this then, and let's see, let's go down here and consider the node part of it first, the node technique. Now here we have 3 different nodes. You can see this, 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 and this. This is all one node right here. And then here's a branch, here's a branch, and here's a branch. So here's a second node. And then here's a branch and here's a branch. So here is a third node. And then down here in the bottom part of the circuit, all of these just simply come together into a single node, and this node is grounded. So let's go ahead then and apply the node technique. Here at node, we'll call this node 1. I don't know if we can keep this in the picture and write at the same time. Let's try it. Okay, node 1. We are going to have then V1 times 1 over 12 plus 1 over 6 plus 1 over 4. And then we will have, for the resistor 4, this is over here at node 2, which we're going to designate as a voltage V2. We'll be determining what V2 is. So let's just say this is at potential V1, the node 2 at voltage V2, and node 3 at voltage V3. So here then we're going to have minus the other end of this resistor is at potential V2, so we have minus 1/4 times V2, and here we have 20 amps going into the node, so we designate that by writing 20 on this side of the equation as a positive number because the 20 amps goes into the node. So there's the equation for node 1. Now let's move on to node 2. And I may have to temporarily put the circuit out of sight. Let's see, can we look at it like this? Okay, node 2, we are going to have V2 times 1 over 4 plus 1 over 6 plus 1 over 1. So V2, and it's 1 over 4 plus 1 over 6 plus 1. And then here, for this resistor, this end of it is at potential V1, so we have minus 1/4 times V1, and for this resistor, this end of it is at potential V3, so we have minus 1 times V3. No current sources here, so the net current for that node is 0. And again, this is the format technique that we're using now that we developed this technique in the previous videos. Now let's go on to node 3. Here we have this resistor and this resistor, so you have V3 times 1 over 2 plus 1. So V3, 1 over 2 plus 1. And for this resistor, this end of it is at potential V2, so we have minus V2. And there's no designated current source for this node, so this is set equal to 0. So here we have our three node equations, three different equations, and we have three unknowns to solve for: voltage V1, voltage V2, and voltage V3. So let's go back to here. Here we have 1/12 plus 1/6 plus 1/4. That comes out to 1/2. And here we have 1/4 plus 1/6 plus 1. That is equal to 17/12. And here we have 1/2 plus 1, that is 3/2. Okay, so let's see. We have 1/2 times V1 minus 1/4 V2 plus 0 times V3. So let's just kind of write these at the top now. 1/2 times V1 minus 1/4 times V2 plus 0 times V3 and that's 20. That's from node 1. Now from node 2 we have minus 1/4 V1 plus 17/12 V2 minus 1 times V3 equals 0, and I'm going to write that at the top. Minus 1/4 V1 plus 17/12 times V2 minus V3 that equals 0. And now from node 3 we have 0 times V1 minus V2 plus 3/2 times V3 equals 0. So there's our three different equations, and now what we do from this point onward is just very repetitious, what you've been seeing us do over and over again in the previous videos. To determine V1, V2, and V3, the first thing we do is make a 3x3 determinant, and we do that by using this column of numbers. We'll call it the V1 column, the V2 column, and the V3 column. So we're going to have 1/2 minus 1/4, 0, and then minus 1/4 plus 17/12 and negative 1, and then finally 0, negative 1, and 3/2. So there's our 3x3 determinant, and let's just very quickly see if we can determine its numerical value. Here then we expand it out using minors, so this is equal to 1/2. And now we're going to get a 2x2 subdeterminant. by covering up the row that 1/2 is in and covering up the column, and we see we have 17/12 and -1 3/2. So let's write that down. Minus the next number that's in the row, and that's -1/4, so that becomes plus 1/4 times this 2 by 2 determinant. Again, cover up the row, cover up the column that 1/4 is in, and we have -1/4 0 and -1 3/2. So let's write it down. And then we have plus 0 times the next 2 by 2 subdeterminant, so that's just 0. So let's see, here we have 17/12 times 3/2 minus 1. Do the arithmetic, and I think that comes out to 9/8. And then here we have 3/2 times minus 1/4. That is minus 3/8. So let's see, this is equal to 9/16 minus 3/8, and this comes out to be equal to 15 divided by 32. So we took the time to go ahead and determine the numerical value for this determinant. Now, to determine the values for V1, V2, and V3, here's how that works out. Here is the 3 by 3 determinant, and we just determined its numerical value. It is 15 divided by 32. Now, to determine the value for V1, we form a different determinant. We replace this column by this column. Remember, this column numbers right here is just simply what the equations were equal to, 20, 0, 0. So replace the V1 column with this column, and that gives us this 3 by 3 matrix, and the value of V1 is equal to the numerical value of that matrix, is really a determinant, the value of that determinant divided by 15 over 32, and that comes out to be equal to 48 volts. Likewise for V2, now we replace the V2 column with 20, 0, 0. That gives us then this 3 by 3 determinant. The V1 column and the V3 column are unchanged. So now, divide the value of that determinant by 15 over 32. V2 comes out to be equal to 16 volts. And finally for V3, we replace the V3 column with 20, 0, 0. The V1 column, the V2 column are unchanged. Determine the value of that determinant, divide it by 15 over 32, and voltage V3 is 10 2/3 volts. So here then, we can write them in. V1 is 48 volts. V2 is 16 volts. And V3 is 10.67 volts. Okay, now what we want to do is go back to our original circuit and analyze it using the mesh current technique. And we're not going to have time to do that in this video, so come back Join us in the next video and we'll finish off the rest of the problem, and then we'll determine the currents and the resistors and compare the two results. Come back and join us for that, and let's finish this problem off.